talking about electrical machines, and I also said that electrical machines are basically energy conversion machines. That is, they use the technology of energy conversion. I've explained what energy is. I said energy is the ability to do work, the ability to effect a change, ability to effect a transformation from one form to another. And I also explained that in mechanical energy, the formula for mechanical energy is E, that is capital E, equals mgh, where m is the mass, g is acceleration of gravity, while h is the height. That is the height. Is it clear to you? And I also explained that electrical energy is also E, equals IVT. Is it clear to you? Electrical energy E equals IVT. Electrical energy E equals IVT, all in capital, where I is the voltage, is the current, V is the voltage, and T is the time. Is it clear to you? So now, having said that, I now explain what is electrical machine. So electrical machine, please write down. An electrical machine is any device that can convert either mechanical energy to electrical energy, e.g. generators, that the generator you are using in your house, all type of generators. When we are talking of generator, people always think that we are always talking of generator they are using in their house to generate power. There are other forms of generators. We have what is called downhole generators that are used in drilling. Is it clear to you? But the most visible type of generator you have is your generator in your house. Like in Nigeria, where there's no light, where the power supply is very erratic and epileptic, everybody have a generator. I just use generator to power my laptop and my phone just now before I started teaching. So that is the type of generator we have. Well, that generator you have in your house, whether small or big, is an electrical machine, and it operates with the principle of energy conversion from mechanical energy to electrical energy. Is that clear? Having said that, electrical machine also convert electrical energy to mechanical energy. Is it clear to you? I've told you that mechanical energy conversion to electrical energy conversion, that is what gives us our generators. That we have generators. That is the principle, that the fundamental principles or fundamental technology principle on which generator manufacturing technology is based. Energy conversion from mechanical energy to electrical energy. If you look at your generator, you see that everything is not electrical. Is it clear to you? If they dismantle your generator in your present, you will see that it's an electromechanical device. It's not just electrical. People will think it's electrical. There are mechanical devices inside. You have them. Then you have the electrical part, like the coil. Is it clear? Which is called the solenoid. You have it. Then the electrical machine also encompasses energy conversion from electrical energy to mechanical energy. Those type of machines are called motor. Is it clear to you? That is why in a vehicle, for example, people call a vehicle motor. The reason why they call it motor, a vehicle is a motor, but a motor, every device, every machine that can rotate is a motor. Is it clear to you? Every device that can rotate is a motor. Please write it down and get it clear. M-O-T-O-R. Any device that rotates is a motor. So a vehicle has rotating parts, like your cars. They have rotating parts, so they call them motor. Now you see that in other mechanical devices, electrical machines, they all have motor, which means they have rotating parts. Like you have pulley system. The pulley system in many machines, like grinding machine, all those other machines, they have. Even you have your grinding machine, your grinding machine that is used to electrical grinding machine. You have mechanical grinding machine that you put fuel inside. It uses the principle of heat and mechanical energy to grind your corn, to grind your pepper, to grind your beans. But you have other machines that are also grinding machines, for example, but they use the principle of electricity. You plug into electricity and it's converted from electricity straight to mechanical energy that is now doing the rotation that grinds your corn, that grinds your pepper, that grinds your beans, and anything you want to grind. Even people during this pandemic, people are grinding. Even in our house here, we are grinding. What is it called? Garlic and ginger and turmeric and all sorts of things. We are grinding it together. Is it clear? So anything that you connect to electricity and it start working like a blender, is it clear to you? Is a motor. I believe I've explained myself very well in the process of trying to introduce what electrical machines are. So I summarize it before I go further by saying that an electrical machine is a device. It's good you understand it. This principle is a device that converts either mechanical energy to electrical energy, e.g., in a generator, or that converts electrical energy to a mechanical energy, e.g., a motor. And I've taken my time to explain the meaning of motor to you. I've explained what motor is. Most of you may not have this experience because you are just starting this engineering class. But with the explanation I've given to you and the life examples I've given, you people will, at the end of this class today, you will appreciate what electrical machines are. Is it clear to you? I've told you that pumping machines in boreholes are electrical machines. Like this one they call semi-submersible. Is it clear to you? Semi-submersible or submersible machines. That one that borehole used to pump water up. It's an electrical machine. I've also told you that a transformer is an electrical machine. I've also told you that grinding engine, the one that uses electricity, you plug it to the wall, to a voltage, a source of voltage, and before you know it, you start grinding your pepper or your tomato or your beans or whatever. Is it clear? It's an electrical machine. But electrical machines are divided into motors and generators, depending on the direction of the energy conversion, whether you are converting from mechanical to electrical or you are converting from electrical to mechanical. I believe that is clear to you. We are in the first slide. So because of our time and because of the number of content we are going to have, I'm going to be very fast. Now I'm going to explain the transformer here, just in a small form. Is it clear to you? Transformer is a topic on its own that before the end of this course, we will find time to explain it better. So I explained to you what is a transformer. Is it clear? So go to that page, on that page one, that first page. I'm seeing the first page. The transformer is an electrical device that is closely related to electrical machines. Is it clear? It converts AC electrical energy to one voltage level to AC electrical energy at another voltage level. Is it clear to you? Now, a transformer is a type of electrical machine. What does it do? It regulates voltage. Is it clear? We are going to do transformer fully as a topic, and I'm going to ask you to draw a transformer. Now a transformer is an AC electrical energy. That is, AC means alternating current. Alternating current is the opposite of direct current. In electricity, we have alternating current, we have direct current. You will be hearing of Michael Faraday. You will be hearing of other scientists that work in the field of electrical energy. What they do is that energy conversion from AC, when the voltage is fluctuating in a up or down, just like when you are playing your stereo, all those ancient stereo, will be seeing the direction of the sound going up or down. Is it clear to you? That is an example of an alternating current. We have a diagram for it. Then we have a direct current. So a transformer converts AC electrical energy at one voltage level to AC electrical energy at another voltage level. I believe you are still following. So what that means is that a transformer can either be a step-up transformer or a step-down transformer. Are you listening? A transformer can either be a step-up transformer or a step-up transformer. Is it clear to you? So I'm going to explain the principle to you. Why I know we are still going to come back to transformer fully, but it's good you understand this principle first before we go higher in our studies. So now as I continue with the class, I'm going to tell you that in a step-down transformer, what it does is that when voltage is too high, the step-down transformer will regulate the voltage by bringing it down. Is it clear to you? It brings it down so that it will not destroy. They call it step down. You will be hearing step down in transformer even in the public. Is it clear? So it converts high voltage to the normal voltage. Now, for example, in Nigeria, the normal voltage for electrical devices is 220 to 240 volts. All machines, go and check your machines in your house. Check your radio, check your television, check your blender, check other devices that you have. You will see that they are regulated from 220 to 240 volts. Now, the voltage that is coming from the source of power, the generators, that is generating companies of Nigeria, Gencos. The voltage that is coming from there could be higher than 220 to 240. 280 volts can be coming from them. Is it clear to you? So what the transformer will do will be to step it down. That is for a step down transformer now. Step it down and regulate it to the normal voltage of 220 to 2 volts, 240, so that electrical appliances in our homes, in our offices, are not destroyed. I believe you got that. That is step down transformer. Now you go to step up transformer. I'm just explaining to you literally, as in theoretically. These things are practicals, and I'm going to give you the practical question that you are going to solve. Now, for step up transformer, is that the direct opposite of step down transformer. In step up transformer, what they are trying to do is to increase voltage. Maybe voltage that is coming is too low, but this step down transformer is basically they are inbuilt into electrical appliances. For example, you have all this equipment, or this electrical equipment that can increase, like stabilizer. You know what it's called, a stabilizer. Most times the voltage that is supplied to your home is so low that you can hardly see with your electric bulb in your sitting room or anywhere, or your passage or your staircase. Now, if it is like that, and you want to watch television, you want to use your refrigerator, then you connect a stabilizer to the source of power. The stabilizer now steps up. Is it clear to you? It now steps up the voltage so that your your devices, for example, a refrigerator, will be able to peak. Your sound system will be able to peak. Every other device that you have will be able to peak. I believe you see. So a step up transformer most times is inbuilt into televisions. Is it clear to you? It's an inbuilt system in some electrical devices, where when the voltage that is supplied to your home is too small, the problem could be coming from the main transformer in the streets, or that is supplying that area. Then you have step up transformers in electrical devices, then things like stabilizer, to boost the voltage so that your devices can function appropriately. I believe that is well understood by all the students. So we are going to push further as we progress in this course. So now, you cannot be talking about a transformer when you are without talking about a magnetic field. Now, at the beginning of this class, I was talking about a magnetic field. Is it clear to you? I just summarized it. What do I mean by magnetic field? I was talking about a solenoid. SOLENOID. You know what's called a solenoid? That is a magnet that is wound with what is it called? Wires, conductors. Most times the wires are brass, they can be bronze, they can be aluminum, but basic, or copper. Is it clear to you? Copper. Now, most generators, they will tell you that if the solenoid is made of copper, it becomes more expensive than other that are made of maybe brass or aluminum. Is it clear to you? So when you wound, that is when you surround, you wind a magnet with a conductor like copper, that it constitutes a magnetic field. A magnetic field, literally, magnetism is another big topic in physics. A magnetic field is a region where the magnetic force can be felt. I don't know if you get the definition. A magnetic field is a region or a space where the magnetic force can be felt. I believe you know that there's magnetic force, you have electrical force, you have mechanical force, you have different type of forces. Is it clear to you? And we know the definition of force. I was teaching mechanical engineering just now, and I said that force is mass as acceleration. We also have electrical force, just as we have electrical power and mechanical power. So a magnetic field, I've explained to you, is a region where a magnetic force can be felt. Now, let me explain this to you further, because I assume that you don't know this, what is magnetism. Now, if you put a bar magnet in your hand, you put a bar magnet in your hand, for example, let's practicalize it now. You put a bar magnet in your hand or on top of a table, and you bring magnetic substances close. You bring magnetic substances close. What do you have? You see that those materials will be attracted to the magnet, so long as they are within the magnetic field. That is the region where the magnetic force is felt. Now, if you put another material, a nail, for example, or a coin, you put it very far from where the bar magnet is, you see that the bar magnet will not attract the coin because it's far. What it means that the magnetic field does not get to that region where they put the coin. So, but all the other magnetic materials, that is material that can be attracted by a magnet, are called magnetic materials. When all those materials are within the region of a magnetic field, you see that they will be attracted to the magnet. So that is what a magnetic field is. Now we are talking about magnetic fields here by way of electricity. Are the fundamental mechanism by which energy is converted from one form to another in motors, generators, and transformers. Please take note of this point I've made. Magnetic fields are the fundamental mechanism by which energy is converted from one form to another in electric motors, in electric generators, and transformers. Is it clear to you? And I've told you that this electric field in electrical motors, in electrical transformers, and electrical generators is represented by a solenoid. Solenoid is a coil. You know what is called coil? In a generator, we have coil. In a, what is it called? A pumping machine, you have coil. That is they called coil, is what is called a solenoid. That is the symbol of electrical magnetic field in electrical machines. I don't know if I'm making a point to you people. Yes, so that is that. Now, 4 basic principles describe how magnetic field are used in these devices. How the 4 basic principles that describe how magnetic field are used in these devices. The devices are electric motor, generators, transformers, etc. I've also told you that the pumping machine in a borehole is also an electric machine. The first principle is a current carrying wire produces a magnetic field in the area around it. Is it clear to you? That is the first principle that they use, this magnetic field principle in electrical machines. Number 1 principle is that a current carrying wire, a wire that is carrying current, produces a magnetic field in the area around that wire. That's number 1. Then number 2 principle is that a time-changing magnetic field induces a voltage in a coil of wire if it passes through the coil. This is the basis of transformer action. You see it? A time-changing magnetic field induces a voltage in a coil of wire if it passes through that coil. This time, what we mean by this one, we are not connected to electric source. So in these things, please take note. When we are talking about magnetic field inducing a voltage in a coil of wire, it does not mean that the voltage is not generated by plugging the device to a power source as at this point. Is it clear? So that is then number 3, a moving wire in the presence of a magnetic field has a voltage induced in it. Now I'm going to explain the meaning of induction to you so that you will not be lost. Since we are not, this is not a physical class that you can ask me questions. So I'm going to explain the meaning of induction to you. What we mean by induction is that induction is the same thing as an influence. Let me say influence. Now, as we are out here now, we are under the influence of many devices. Now we are under the influence of gravity. We human beings, we are under the influence of gravity. We are under the influence of different forces. Is it clear to you? We are under the influence of different forces as we are living. Is it clear to you? So now I'm going to give a practical example of induction for you to understand. This one was done by there's nobody that goes through primary school that will not understand this process I want to explain now. Now, for example, take your biro. Is it clear to you? Take your biro. This is static electricity in action. You rub your biro vigorously on your hair. For people that have hair, thick hair, woolly hair, you rub it vigorously on your hair. If you rub a biro, for example, a bic, for example, you rub it vigorously on your hair or on woolly materials. You know what's called wool? Wool is a textile material. You rub it vigorously on wool. What do you have? That your pen will be able to pick pieces of paper, small pieces of paper that you have cut on top of a table. That that your pen will be able to pick it. If some of you have done this experiment before in primary school, you will understand what I'm talking about. If we were in a class, I would have done it for you practically. Is it clear to you? Now, the pen does not touch the material, but it will be influencing it. The plate of paper, the small piece of paper you have cut down will be moving up and down. What that is an induction, induce magnetism. Is it clear to you? So I've explained the meaning of induction to you, so that you will not say you don't know what we mean by induction. Is it clear? So that is that. I'm coming. Yeah. So that is the meaning of induction. Now I said number 3 principle on which all this electrical machine is based. I've given you different principles. I've given you number 1 to number 3 principle, where I was talking about induction, voltage induced in it. So just as you can induce magnetism, you can equally induce voltage. You can equally induce voltage. This is the basis of generator action. The generator you are using, those generators we are using in our homes, they use this number 3 principle. Then we have the 4th principle of electrical machine, which is a current carrying wire. A current carrying wire in the presence of a magnetic field. That's why I was talking about solenoids. A current carrying wire in the presence of a magnetic field has a force induced on it. This is the basis of electric motors. The action of electric motors. They use this principle of a current carrying wire in the presence of a magnetic field. Is it clear? While for generators, a moving wire in the presence of a magnetic field has voltage induced in it. This one has force induced in it. So you can see the different principles. So we leave that point now. We leave that point now and go higher. Now we are now in page 3. We are talking about magnetic field sources. Without a magnetic field, we cannot be talking of electric machines. From the 4 principles I've given to you, you have seen the 4 principles I've given to you, that without a magnetic field, you cannot be talking of electric motors. You cannot be talking of transformers. You can't be talking of what is it called, a pumping machine in a borehole. You can't be talking about all those things. Now, these things are in physics textbooks. You will see them in physics textbooks. There's no magic here. There's no rocket science here. Everything here you will see them in advanced level physics textbooks. So now, the magnetic field sources. That is the 2nd page. A current carrying wire produces a magnetic field in the area around it. That is an induction. I've explained the meaning of induction to you. Now, if you look at that magnet on page 2, you will see that a magnet has both what is called the poles. A magnet has the north pole and the south pole. Is it clear? Every magnet. Now, a magnet is a wonderful substance in nature, in that when you cut a magnet into 2, a magnet that already has a north and a south pole, when you cut it into 2, that part you have cut into 2 will also have a north and a south pole. Keep cutting a magnet into pieces. As you continue cutting the magnet into pieces, they will continue to have north and south pole. That has been the wonder of science. Over the ages, scientists have wondered how come it is like that, but it is always like that. Is it clear to you? Now, I've explained to you that the magnet has a north and a south pole. Now, when you bring magnetic substances that can be attracted by a magnet, metallic objects, for example, when you bring them close to a magnet, they will be attracted to both the north and the south pole of the magnet. Is it clear to you? Now, we have what is called a right-hand rule there. Direction of current and direction of magnetic field. They move in opposite direction. Is it clear to you? Now, you can see here now that in that page 2, that there is where we develop what is called the Fleming right-hand rule or left-hand rule. Is it clear to you? In physics, we are going to get to that. Now, the direction of current and the direction of the magnetic field are at variance. Is it clear to you? They move in different directions. So that is the basis of what we call solenoid or a magnetic field. Now we have magnetic circuits. I did not say magnetic circuit there. That is a transformer, an example of a transformer. You are saying in page 3, you will see a magnetic circuit. Now you are seeing the solenoid. You see what is called N turns, the number of turns. You have a material there in form of a rectangle. You have the wires that are connected to it. It could be copper wire, please. It could be aluminium, but in most instances they use copper wire. as the wire that is carrying the current. Is it clear? They use copper. Copper is the most used. If you open your radio, you open your television, you open most of the electrical devices, you will see the solenoid there, the magnetic circuit there, where you see all this shiny copper wire. Those wires shining, you will see them. Is it clear to you? So now you have the end turns, then you have the cross-sectional area, then you have the mean path length there. So you have an analogy between magnetic and electric circuits. You have a magnetic circuit, you have an electric circuit. Now, in electric circuit, you have the resistance. You know this one from time. That current is voltage over resistance. If you look at that electrical circuit there, you are going to see, now take note that electrical circuit, we have them in series, we have them in parallel. You should know those one in your electricity in secondary school. Is it clear to you? Electric circuit can either be in parallel or in series. When they are in series, you calculate the resistance differently, and when they're in parallel, you calculate the resistance differently. Now, when electrical circuits are in series, the effective series is R1 plus R2 plus R3 down to Rn. Is it clear to you? But when they are in parallel, the effective resistance is 1 over R1 plus 1 over R2 plus 1 over R3, that's to 1 over Rn. Is it clear to you? Now, we are trying to compare magnetic circuit with electric circuit. The two of them must work together for electrical machines to work. Is it clear to you? So that is that. Now, the basic law governing the production of magnetic field is given by the current by a current is the Ampere's law. Is it clear to you? The Ampere's law. That is the basic rule that is used in production of magnetic field. The Ampere's law. Yes. Now you have magnetic field intensity. Magnetic field intensity. Right? That is the power, the number of turns. That is the magnetic field intensity is determined by the number of turns. That is how you wound the copper wire around the magnet. Did you use a lot of it or you just use small? Is it clear? You should appreciate what I'm telling you now. If you wound a lot of copper wire around the magnet, then the magnetic field intensity will be very high. Is it clear to you? So now you also have the current passing through the coil. We have the number of coil turns. Then DL is the differential element of length along the path of integration. Is it clear to you? So that is that about that. So we are going to push higher as we still have time. We are now in page 4. We are in page 4. In page 4, we are still illustrating electric circuit and magnetic circuit, how they relate to produce power in generators, in electric motors, in what do they call again, in transformers, and in pumping machines and other electrical machines. Is it clear to you? So now we are now in the fourth slide. We are in the fourth slide. In this fourth slide, that is page 5, we have the basis of transformer action. Faraday's law of induced voltage. Is it clear to you? Now, from a time-changing magnetic field, you are going to see there. Now, Faraday's law, we know that Michael Faraday is one of the fathers of modern electricity. So he gave us a law that is referred to as Faraday's law. States that if a flux passes through a turn of a coil of wire, you know that by now you don't need to be told, you already understand what we mean by a coil of wire. That is when you wound copper wire around a material. Now I have a pen in my hand here. Now, if you appreciate what I mean by a coil, if you have ever seen a thread before, this thread that tailors use, either black thread or white thread or green thread or thread of any color, you see that thread is wound around a material, a paper, something like a paper. They wound it around it. Is it clear to you? That is an example of a coil. In case for those that don't understand it up to now. Now, if you are in page 5, you actually see something like what is it called? This thread that tailors use when they want to when they are sewing clothes. They put it on top of the machine and it will be rolling. You will see a coil there, but you can see that the wound is just once. Now there's a way we can wound it around that you cannot see that material again. So I'm going to define Faraday's law again for you and do some explanations before I give you your assignment. Then we will close for today. Now, Faraday's law states that if a flux passes through a turn of coil of wire, I've explained what is meant by coil of wire. I've also used what is it called, thread to illustrate it. If Faraday's law states that if a flux passes through a turn of a coil of wire, a voltage will be induced in the turn of wire that is directly proportional to the rate of change in the flux with respect to time. Is it clear to you? Now you have the illustration there, E induced at N over the N dt. Is it clear to you? Now, induced voltage at a coil terminal is that is E. You will see E, there's small letter E equals N over D over dt, where E is the induced voltage at coil terminal. You know the coil now. When you wound wire around maybe a stick, but you don't use stick, please. We use the conductor. A stick is not a conductor; it's an insulator. Around the conductor, you are going to have a voltage induced at the coil terminal, which is the edge, both ends. Then the N is the number of turns of wire in a coil. Then that symbol there is flux passing through the coil. Is it clear to you? So the minus sign is an expression of Lenz's law. Lenz's law states that I'm going to give all these things to you today as an assignment, so that you will understand it better. When you go to physics textbooks, you explain them, you understand. When I do this now, I'm going to explain the last part to you. Yeah, Lenz's law states that the direction, please, you can go now, states that the direction of the voltage built up in the coil is such that if the coil ends were short-circuited, it will produce a current that would cause a flux opposite the original flux change. I come again, Lenz's law. We are going to, if you go to O-level textbook, you will see there. This one is an advanced level material. So Lenz's law, Lenz is L-E-N-Z, apostrophe then X, law. Lenz's law states that the direction of the voltage build up in the coil is such that if the coil ends and the end of the coils were short-circuited, know what we mean by to short-circuit? Is it clear? We're short-circuited, it will produce current that would cause a flux opposite the original flux change. Now, that is that about Lenz's law. Now, we are going to go back to Faraday's law for you to understand Faraday's law better before I give my assignment for today. Now, practicalizing Faraday's law, you see a coil there that is wound on a conductor. I believe you are seeing it. You see a coil there. That coil is connected to a voltmeter. Are you seeing a voltmeter there? That is not an ammeter. Neither is that a galvanometer. That is a voltmeter to measure voltage. So when you wound a coil, that is a copper wire around that conductor, you now bring a magnet in, a voltage will be induced. You will measure with the voltmeter there. Is it clear to you? So that is what we mean by that. Is what when we state that Faraday's law, that if a flux passes through a coil of wire, a voltage will be induced in the turn of the wire that is directly proportional to the rate of change in the flux with respect to time. You see it? That is the illustration there in that flux that is connected around the wire, the conductor. Then the conductor, the flux of wire or the coil of wire is connected to a voltmeter at the back. There's a way you connect it. Then when you bring the magnet in, the north pole of the magnet is entering the coil of wire now. The wire, that is the solenoid. Let me call it solenoid. I've explained the meaning of solenoid before. Then you are going to have what is called you are going to have an induced voltage that is going to be measured by the voltmeter. You are seeing it there. So before my time will elapse, let me quickly give you an assignment for today. You are going to give me number one assignment. You are going to state Faraday's law. Faraday's law. Then number two, Faraday's law with examples, not just state the law. This is must be practicalized. State Faraday's law with examples. With examples. With examples. Then two, state Lenz's law. State Lenz's law. State Lenz's law with examples. Please go to physics textbooks with examples. Then number 3, explain the working principles of a transformer. Explain the working principles. Explain the working principles of a transformer. Then you are going to draw the sketch with a sketch. Explain the working principle of a transformer with a sketch in brackets with a sketch. Then you are going to draw a transformer, the sketch of it. Is it clear to you? That is the assignment for today. So as we still have some time, we are going to continue with this particular slide, which is slide 5. The slide 5, we are still explaining the slide 5. Now you see the illustration there that instead of the moving magnet, if a time varying current is passed through the coil, that is, instead of using a magnet, then we have a time varying current. That is current that is changing with time. And you know current can be measured. Current is measured in ampere. So you are using a time. You can see the illustration down here. The illustration of is down here where you are using a time varying current is passed through the coil. A time changing flux is produced, which when transferred to another coil induces a voltage across the terminals. You can see the measurement there. They are using an ammeter to measure they use an ammeter there to measure the current. This is the basis of the transformer action, which transforms the voltage level according to the nature of turns in each coil. Is it clear to you? So now, finally, before we end this class, a transformer that is going to do step up must have, at the primary coil, at the primary side, is going to have fewer turns or coils, while at the secondary section is going to have more turns. I don't know if you follow. A transformer that is going to do step up, a transformer has two sides. You have the primary coil and the secondary coil, or the primary turn and the secondary turn. The primary turn is illustrated with small letter n, while the secondary turn is illustrated with capital letter N. Is it clear to you? So now, if a transformer is going to be a step-down transformer, then at the primary coil section, then the number of turns should be very few, while the secondary side is going to be very large. Then, if the transformer is going to be a step-down transformer, I've explained the difference between a step-down transformer and a step-up transformer. It's going to be a step-up transformer, a step-down transformer, then at the primary side, it's going to have more turns, more wound of copper wire or whatever wire you want to use compared to the secondary side. Is it clear? So that is the basis of a transformer. So I explained this assignment to you again. I said your assignment for today, I said state Faraday's law with examples. Number 1. Number 2, I said state Lenz's law with examples. Number 3, I said explain the working principles of a transformer with a sketch. I believe the assignment is well understood, and you will do well if you submit it to ofsn2002@yahoo.com. If there's any problem, my phone number is 08037706023. So for those that didn't get the assignment well, you can always send me a message on WhatsApp or by any mode of communication. Thank you very much for listening, and we're going to meet here again on Thursday for our next class, where we're going to be talking about technical mechanics and also electrical machines. Yes, so when we come back, we are going to be talking about, the transformer today. We'll talk about transformer today. We are going to be talking about generator action. Sorry, what is that? We'll talk about transformer action. We are going to talk about generator action. Then we'll talk about electric motor. Then any other thing that is not even inside these slides, I'm going to bring them and also talk about them. I believe that is clear to everybody. So